I would like to show about how to use Sutra model to simulate the recharge of groundwater as a result of ponding formed on the surface, and later on how the recharge would bulge the water table, and eventually the bulged water table will be dissipated to the ambient environment. So this is a figure showing in the flat plane where the pond is artificially formed by pumping water. As you can see, the pipe going there. So we pumped roughly 30 of the volume. We pumped about 65 megaliters, which is equivalent of 40 standard swimming pool volume of water, so which is significant. And what we find is that the water table is about 5 meters below the surface, and that is being bulged, increased. And so the water table under the pond is increased, but the ambient environment is still the original water table. And that means the groundwater will dissipate as it goes away from the pond and eventually become a flattened value, a flattened water table. So here is the cross section of the pond. So the pond is located here. So we've got two pressure the balls to monitor the water table. And what we find here is, which is very important here, is that it's a confined aquifer. So originally it has got 3 layers: silt layer near the surface, clay layer which is impermeable in between the top layer and bottom layer. The sandy layer is fully water saturated. Once we have the ball constructed, what we find is that the pressure, the water level just increases from 5 meters below the surface to 2.8 meters below the surface, which is the indication that the groundwater table is a confined water table. And another important thing here is that the water table at all those locations are the same, which means that there is no groundwater table, groundwater level higher in one side of the pond as compared to the other, which is very important for us to be able to use a radical 2D model to simulate the pond impact. So how does the radical 2D works? So this is the pond that is formed by recharge, by pumping, that creates a pond near the surface. And we try to simulate basically from A to B. So A is at the center of the pond, and B is outside of the pond. So here is A and here is B. And the distance from A to B is roughly 150 meters. But within the 150 meters, we know that the boundary of the pond is from the center of the pond to about 100 meters away from the pond. So one of the important things to use a radical 2D method is that the thickness of each location is equal to 2 pi x, where pi is the distance from any locations to A. So let's say if it's here, then the x is going to be starting from where the cursor is to A, and the thickness is 2 pi x. So by doing that, we are basically able to simulate the vertical profile of the entire pond. And remember, the reason we are able to use this method is because the groundwater level on outside of the pond is almost a constant value. If the head in one side is higher than the other, then we have to use 3D model, which could be very time consuming. So to be able to emulate the multiple layers, we've got the silty layers, which is about 5 meters. And then we've got the sandy layers, which is 2 meters. So in terms of the boundary settings, we know that there will be no flow at the bottom. There will also be no flow from the center because of what we call hydrological divide. And from the boundary here, we know that there is no lateral flow, so here is no flow applied to the COT layers. But we apply a hydrostatic pressure at the sandy aquifer. So just in case if the head here, so originally head is water level is a constant value, but once the water pressure, once the height increased under the pond, then we are expecting water moving from the left-hand side to the right-hand side and then left from here. But once the recharge stops, we will see that the water level becomes almost a constant value. One of the extra thing that we also made a approximation is that although the surface layer is sealed, we find that the flow is quite fast within this layer, which is due to the existence of cracks and preferential pathways, which are potentially formed by desiccation and existence of the vegetation roots. So by doing that, we need to ensure that the permeability of this layer is relatively high, plus that the porosity of this layer is very small. So the reason that we don't use the bulk permeability is because the wetting front never aimed to saturate all the COT layers. It only saturates the conduits where preferential pathways are taking place. So in that case, using bulk porosity does not represent how the recharge is passing through the thick sealed layers. The third thing, which is also quite important, is that we basically ignore the soil water retention effects within the COT layers. And this is because if we apply a very large sealed layer soil water retention curve, then we know that here is going to be saturated, and eventually the pressure, the saturation near the surface is almost close to saturation, given that there's only 5 meters, and sealed layer we know that it has a relatively steep soil water retention curve, so that the under hydrostatic pressure distribution, the surface saturation is about, let's say, more than 50%, but this is not the case. So we basically assume that there is no change of relative permeability as a result of the unsaturated zone. So that's the settings. So if we look at the result, what it looks like is that when you look at the saturation, originally the surface saturation are relatively high, and at the very bottom it is almost no water. But because the permeability in between these layers are relatively high, and also the gravity effect, the water in the pond started dropping down to recharge the water table, and that allows the water table rises. And it rises in a relatively high elevation. And this high elevation makes the pressure in the pond higher than the ambient environment. And then it started dissipating from the pond to the ambient environment. And because the surface water is fresh, the fresh water actually push the salts to the other side, to the outside of the pond as well. But eventually, as the surface water depletes, we will see that the bulged water table drops down, and the mixing zone between fresh water and salt water gets widened. But eventually what we expect the situation is exactly the same as original condition, where the water table is flattened and this fresh section of groundwater will be backfilled by the salt water. So that's basically how the simulation looks like. Now, we are going to simulate the whole process using a suite of tools. So the tools that we are going to use is SUTRASET. So SUTRASET is basically based on USGS SUTRA with extra functions to implement evaporation, seawater inundation, and tide. So those processes. This is written in Fortran, so we will need to have a very good tool to pre-process and post-process the data. So by doing that, we need to use SUTRALAB. SUTRALAB is basically a MATLAB-based pre- and post-processing for Sutra. So we basically use that tool set to construct the models and do the post-analysis to produce exactly the result as you see from the PowerPoint. And the other thing is that I have a repository within GitHub called eWatering, and that eWatering has got all the pre and post processing script to produce the simulate result. So just be aware of that. We need to use these 3 packages, and these 3 packages are all downloaded from GitHub. So now we need to extract those things. Before we extract under Linux environment, we need to download a software called MinGW. So that's the name. What does MinGW here do is that it provides an open source Fortran compiler, which is called gfortran, and make. So those 2 functions, commands, are very popular in Linux environments, but you need to have a Windows version. And those 2 are all included with a package called MinGW. So to be able to download that, I suggest you just type MinGW, and then you would be able to get a top one that is MinGW and W64. So you got quite a few different MinGW. So to single out some of the things, so Arch Linux, Debian, Fedora, those ones are for Linux, and there are Mac operating system based as well, which are not the ones that we're after. So the key thing that we need to know is the difference between this is SideWing and MinGW. So these 2 both works for Windows system. Which one are we going to use? So the difference between SideWing and MinGW is that MinGW is able to compile the Fortran to an exe file that Windows can run. So once you got that exe, you can double click and be able to run the command. The SideWing basically is another operating system within Windows. So once you use SideWing to compile your source code, you basically end up with an executional file that can only run within SideWing. So if you double click through a Windows browser, you wouldn't be able to run the command because that's for the SideWing system. So in that case, if you want to get a relatively local binary executable, I would suggest you to use MinGW builds. So that's where you have, and then you download that file. So I've already downloaded that file and installed. So this is the way how you do that. And now let's assume we've already installed. It's probably sits within here, this folder. So as a default folder. So let's go there, and then you will be able to see a BAT file called MinGW-w64.bat. So that's where you're going to double click, and you end up with a command interface here. So I'm trying to see whether we can enlarge the font size to make it relatively easier to read. Okay, so that's better. Now we are at C, so we need to go to a folder. Let's say cd. So let's make a directory. Make directory eWatering. Okay, so now we've got the eWatering. So we can cd into eWatering. And then to be able to see what is inside directory, we can't use ls anymore. So a lot of people knows that we use ls to check what is inside. In Windows system, because it's not POSIX, so let's assume that POSIX is something like English. But Windows is not really an English-based language. It's actually called Spanish. So it doesn't use ls, this type of commands. Instead, you have to use dir. So that's basically to check a command to check what is within the folders. It's a bit unfortunate that Windows does not speak an English equivalent language because it doesn't follow POSIX rule. But nevertheless, just getting used to it. So now we need to basically download the three files, the three packages, SUTRASET, SUTRALAB, and eWatering. And we know that you could use, if you go to SUTRASET, you search SUTRASET, you will be able to find out the GitHub page. You could also download the code, download the zip file and extract it. But I'm not suggesting you to do that because this program is keeping on updating. So some of the files are 6 years ago, some of them are 2 years ago, and some of them are only 30 seconds ago. So if you use Git to track it, you only have one instance within your computer. You don't go to any other ones. You don't have to say SUTRASET 1, SUTRASET 2. It's pretty much like you write a report, you always have final version, and after you return from your supervisor, it's final 2, final 4, final 5. It doesn't really have to have that. You only have one instance, and then you track every single time the changes. So you copy the location by right-click and copy, and then go to the command prompt, and then you can say git clone. And to be able to paste, you just simply use the right-click. Then you are able to clone SUTRASET to your local computer. So SUTRASET is downloaded. Now you're gonna do the same thing for SUTRALAB. SUTRALAB. So again, you copy the address, and then just use that to be able to download the SUTRALAB in your local folders. The third package is the commands to be able to get the code, which basically is in my repository called eWatering. So if I go to my GitHub account, probably I just do eWatering and see whether there's anything coming up yet. No, this is actually just I probably need to go here, eWatering, to see. Okay, there you go. So then you copy the whole thing, paste it, and git clone, and then right click, and then you are able to get eWatering. Now if you use dir, you will be able to see that SUTRASET, SUTRALAB, and eWatering are all there within your folder called eWatering. There's an important thing to do before you need to be able to use these packages, is to allow Windows, is to tell Windows where are those folders. So to be able to do that, we need to do cd SUTRALAB. So here I can just do SUT and use a tab to finish the whole word, and then we arrived at where the SUTRALAB is located. So now we need to tell the computer where SUTRALAB is located. So the way of doing it is to go to your My Computer, right click, and this one doesn't really work. So we need to go to your desktop and then this PC, properties, and then use advanced system settings. And here we've got the environmental variables, right? Now I do have some of the previous SUTRALAB and SUTRASET, but now I'm going to change it to the one that I just downloaded. So this one would call eWatering, right? And then click, and I also have SUTRASET that has got e-watering SUTRASET, right? Okay, so now SUTRALAB and SUTRASET, all non-capital, is being directed to the specific location where they are. This is very important because in general, you can just use the variable to tell where are they rather than go to the individual folders. And every computer has different folder location, and that will make your code compatible when you move a computer A to a computer B. So now I select the OK. I probably have to reboot my MATLAB. So if I use system in env and SUTRALAB, you can see that I'll get env. It's get in env. So that's basically still the original location. So if I switch it off and switch it back on, so let's do the OK. And we probably can get the new environment variables. So it just takes a bit of time to be able to run. Okay, so now if I just do the get environment, you will see it's already been changed to the new location where SUTRALAB is, right? Now, it's good that the computer is already know where SUTRALAB is, but MATLAB doesn't know. So you need to let MATLAB know where SUTRALAB is. So to be able to do that, you will need to run a command called C SUTRALAB and M files SL set path. So you need to run this whole command, right? After you run that, you will realize that MATLAB is already known some of the SUTRALAB commands. Say, for example, read NOD. You see now if I finish read N and then use tab, they know read NOD, which means MATLAB already know where SUTRALAB library is located. Okay, let's put that on a side. We have one extra thing to do. Remember that we are going to use SUTRASET to run the program. But currently, SUTRASET is nothing but the source code, which is located as src. See, these F files are basically all the source code for SUTRASET. But these source code are not able to be executed. It's not a binary file. We need to combine them, compile them into a binary executable so that we can run it. So if you are using a Linux system, then we probably can use make. But given currently we are using a Linux-based system, Windows-based system, which is not POSIX, we need to use a make that is for MinGW. So this is the command. So I need to tell them that this is basically to create a file that is based on Windows, right? So then after this, I will be able to create a G version F90. And this G version basically tell which version of SUTRASET am I running. So this is very useful when you have 500 upgrades of the SUTRASET and still you know which version you used for run the current results. Anyway, so when you create the G version, you just use MinGW-32-make all. Then you will be able to see that the SUTRASET has been compiled to object files first, and then to a binary form that is called SUTRASET _ GF. So let's just wait patiently a little bit so that you will see Now if I use DAR underscore, you will see all the object files is being created, but the most importantly, I've got SUTRASET GF. You could run that program. It just said that the input file does not exist, so which means the compile is very successful. So now we've got the engine that is already there to be able to do the work. So now we've got several things that is being ready. So SUTRALAB is already being recognized by a MATLAB, and SUTRASET has got the binary file readily to be used. And now we could move to the list of MATLAB commands to be able to create the models, which is located in e-watering. So I moved to e-watering modeling benchmark. And here we've got quite a few files here. So the sequence of running it is first use the write input, SL write input, to be able to get the original input files, and then we can run SUTRASET. And after we run SUTRASET, we can read the output and then analyze the output. So basically this four will be executed. So to make a start, I will first run SL write input. Basically, after run that, you will see you create Sutra file, part 1 IMP and part 1 ICS. So the one of IMP is the input file, ICS is the initial condition, and ET-IMP has got some parameters inside related to evaporation and also relative permeability. And after I have these files, I'm able to run SUTRASET. So now it's executing. It takes about 2 minutes, but it doesn't really matter because we can basically talk about what is written in the files, so that we can later on come back and see what does these things mean. Okay, so now we need to introduce what is the pre-processing commands, which is written in SL underscore write underscore input. So first of all, remember always clear and close, because if you don't do that, sometimes your previous simulation will affect your current simulation, and you don't want that to take place. So you really need to clear everything. And I also create a C constant object so that you can get all those 9.8 as gravity, and also grams to kilograms, those kind of variable, this kind of unit conversions. I always recommend to use a variable to record all those unit conversions, so that in your program you will never have many numbers. The problem for the numbers is that after 5 years you forget what does the number mean. But if you make a very valid variable, you can always remember that. So let's say this program was done 2 months ago, and I still be able to remember vividly that which one is used for what. So this is a very good exercise that I suggest everyone to do. So this one is still running, so we can keep going. And then later on, we create a Sutra file object. So we're not reading from any files, it's creating from scratch. So we say read from file, no. Now we create those tiny objects, that's IMP file, which for inputs with a unit or file number 50. This can be random number, so don't worry about that. It doesn't affect the simulation result. It's just that you don't want to write two things into one file. ICS file is the initial condition. So initial pressure, initial concentrations. List file is the basic summary of the simulations. The RST file is for hot start, which means that you can, if you need to simulate, say, for 2 years, you can run for the first year and save into a IST, and then just keep going from the end of the first year to the end of the second year, So that's very useful when you want to continue with your previous simulations. NOD files are the file to store all the node-based results, particularly for pressure, saturation, concentration, temperature, and so on. So the ELE file is basically the element-based result. For example, like flow, permeability, this type of outputs. And the OBS file is basically our observation file, so you can specify a location so that the pressure or the flow will be extracted every single time step. The summary file is basically to show how the simulation is converged or not. So it has got all the converged information here. BCOF is basically source and sink boundaries. So if you got a boundary that you want to pump water in, that's going to be stored in the BCOF. BCOS is basically a source and sink for the solute. So it's pretty much like if we add 1 kilo of salts inside our aquifer, and the salt is just solid salt. The BCOP is basically a fixed head boundary condition. So let's say if you have a Marriott bottle and you use Marriott bottle to control the water level, and BCOP is basically what the output will be located. The BCOU is a constant concentration boundary. So you could understand that by you putting a huge pile of salt, solid salt, on the surface so that the concentration on that cell is always the same. So that's basically being implemented by the BCOU, right? So I think probably the simulation is already being completed. So that takes about 3 minutes to run. And now we can SL read and SL analyze. Remember, those commands are only available when you have SUTRALAB added into your library. So you see it's now plotting results. And we just let it go, and then we keep on explaining about what the input conditions, the input data means. So after you create these ones, you export that, you write down into a file. Right, here are some of the common variables. So let's say concentration of water is kilos per salts per kilos of solution. So for seawater, it's actually 0.035. Fresh water, instead of putting a 0, I would suggest you to put a very small number. The reason that we don't put it as 0 is because sometimes there are some kind of numerical oscillations. So let's say if you have a 0, the oscillation could change the value from a negative number like this to a very small positive number, right? But the problem is that if your concentration becomes a negative number, it doesn't have any physical meaning. Whereas if you change to this type of base number, so it probably will fluctuate between this number, which is meaningful, and probably that number, which is also meaningful, right? So you want the numerical oscillation is fluctuating between these two values rather than these two, because this as a concentration doesn't make sense. So remember, never use 0 to consider as your background concentration here. Now, the initial head in the aquifer is negative 4.8 meters. So I always have a way to use my variables. So I try to use as many words as possible to tell what this means. So even if it's none, that's okay, because I know exactly what that one is for. And I also put the numbers here. So if you got a P, that P is basically the separator between the numerator and denominator, so that you can do unit conversions. You also got the initial pond water depth as meters is 0.5 meters. So remember that the initial sealed layer pressure is about -5 power 4. So it's a it has a relatively high suction. The moisture content there is obviously very low. The sealed layer permeability is about 5 power -15. And the sand layers has a relatively high permeability, so that number. The radius of the pond is about 100.1. You could ignore the 1, but I usually use that to ensure that the node located at 100 is going to be included. So I usually use that small tricks to include the node that is located at 100 point. I think the analysis is pretty much finished, so we can go there and have a look at the simulation result. So let's say we go here and then go here. You can see that we've got a AVI file that looks exactly, oh, that's not quite right, but there's kind of very interesting, that's very strange why this graph doesn't look 100% correct and same as what we did before. We probably just net it wrong again, and maybe they will figure it out. Also, we can try to see the individual PNG files to see the same problem appears. Okay, let's just run it again and see whether that problem could be resolved by itself. So just do a SL analyze. They still have this kind of issues here, but that doesn't matter. So it's just a visualization issue which we can resolve later on. Now we've got the dx and dy. Dx is the spatial distance between each node. Dy is the vertical direction, and dz is basically the width. Remember, in this graph, we said that the z is equal to 2 pi x. X is the distance from that point to the central of the pond. And then we've got the X array using a very straightforward command imbuing in MATLAB to be able to create an array. So one of the things that I normally do, particularly by debugging, so let me see whether this one is completed. So once this is completed, I can show you how this works. Is a debugging process. So let's leave that for now. Which is that you could click the dash next to the number, then you are able to create a red dot, and then you could use run, and after click run you will see an arrow next to the red dot, which means that all the scripts above the arrow has been executed. So these ones are all being executed, but this line is ready to be executed. So a way to test that is to go in here, and if you just use dx, you will see that dx is not defined because that line has yet been executed. But you can, if you do pond radius meters, you will see that it's already been defined as 100.1. And then what you could do is that you could use step, which only run one line. So now dx is being declared, but dy is ready to be declared. So in that case, you can do a bit debugging to check where is the problem. Also, the workspace here is able to tell you all the declared variables, and you can see from here whether this is what you would like to see. Anyway, so now we are in dy, so we can use this as a good way to show where we are. So dy is basically the vertical direction, and the dz, we first use a 1 here as a start, and later on we need to change it. So the X array, as said, is going to be a array from 0 to 150 with a interval of 1. So basically that is going to be 0, 1, 2, 3, 4 up to 150. So we could do that here. Oh, it's not being executed yet, so we need to do a step. And then you are able to see that's basically what the variable looks like. And then the Y array is being done in the same way. So it starts from -10, which is the bottom, which is here, to the surface. So basically Z and Y starting from bottom and then going all the way up, right? Now, so that is also being created. And then we need to tell how many x-axis in the how many node in the x direction and how many node in the y direction. So that could be done by using a length function, right? Now, remember that this way will create a kind of rectangular grid, which looks like a pretty much like a table. So if I insert a table, so let's say I create a 3 times 3 table, you will find that the node which is at the corner is going to be 4. But the element, which is the block, is actually the node number minus 1. So if it's 4 node, the element is 3, and likewise in the vertical directions. So that's why we've got the NEX. The NEX is the number of element in the x direction, which is the length of the node number minus 1. Yeah. Now this is the interesting part. Remember that we have created the arrays, but now we need to create a matrix. So basically, using mesh grid is able to create a matrix, which are the x-axis for all x coordinate of all the nodes and a y coordinate of all the nodes. So if we run that, you'll be able to see you create a huge matrix. So this is the x-axis. So you can see that it's very regular. 0, 1, 2, 3, 4, 5, 6, 7, 9, 10, up to 150. So basically all the x-axis is being created by this command, which is pretty convenient. Now, we could also do that for the y not matrix. Okay, so remember those are the y-axis for the node. But there is one very important thing here. So you see that somehow the direction is reversed. So if we consider this is our matrix, the bottom coordinate is going to be -10, whereas the surface is supposed to be 1, correct? So it's somehow being reversed. It doesn't really reflect how we actually see the aquifer, so it's upside down. Just bear that in mind. This is very important. That's why we need to flip this x and y in our calculations here. So the second thing that we need to find out is the keynodes. So we first create an empty keynodes, and then we are able to basically create the cell dx, the dx of the cell. It's very important to tell what does cell here mean in Sutra. So we've already discussed that at every single point, that is called a node. The whole block is called element. But in Sutra, there is an extra definition that is called a cell. So the cell basically splits it has the same number as the number of node and assign the node into a finite volume. So now I'm trying to show you how the cell looks like if we have 3 times 3 system. So because currently the node doesn't really have a volume, but cell does. Now you can see that for every single node, it has got a specific volume associated to the node. So this is cell 1, cell 2, cell 3, and cell 4. And likewise, you've got another cell, 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 and cell. So the number of the cell is the same as the number of node. But the difference is that when you got a cell, you got a finite volume. But you don't have a volume when you're talking about a node. The element has got volume as well. But an element is an add up of several cells, as you can see here. So that's the cell. We basically calculate the cell, the dx of the cells, which you can see from the command here. So we probably can do that and then make this one small. And that basically tells your dx of the cells. And the dx for the very first one, that is only half, but the rest of them are all 1. You see the very first one is half of the dx, but the rest of them 0.1, but the very last row has got 0.5. Right? So likewise, that's the dx. And also it also happens for the dy as well. So we basically just pass that. Now, in terms of the total number of nodes, that's nx equal to ny. The total number of elements is nx minus 1 times ny minus 1. So we don't really have any issues there. Now we need to create a indices for all the nodes. So we basically create an array. And to be able to make this from a row to column, we add a apostrophe. So if you look at the II, it's basically a vertical array with the total indices of each node, which we will be used later on. Now, if you look at the X0 array, which is basically convert the X0 matrix to an array. So this is the way how you do that. So remember that X0 array has got a matrix, but in MATLAB, it's starting from column and then rows. So the way of understanding that is if A is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, which is a matrix, you will see that A2 is actually 4, not 2, because in the memory, it's being stored in this way. Vertical column first and column first and row second. Sorry, row first and column second, right? So by doing that, you can convert the whole NOT matrix into an array, which can be used to write down in the text files, right? Okay, so that is down. Now, you also do a reshape of the II, because remember the II is an array, and we want to make it like a matrix so that is visualizable as a matrix. What you can see here is something pretty much like what we see the whole aquifer, right? So it has got a vertical, has got rows and columns. But remember, there is an issue. We're starting from the bottom and then going further way up, right? Again, the bottom is at the top and the top is at the bottom. So we need to really flip it to ensure what is the real conditions, right? So bear that in mind. This is very, very important. Now, if we keep going with the command, that's what we are doing. So node index matrix, still node index matrix, but I do a gravity compensated, which means we flip it. And the flip makes the whole matrix in a very visualizable way. So if it's on the top, So if I show that, you will see particularly for the first row, 0 starting from bottom all the way up, and then bottom all the way up, bottom all the way up. If it's lower, that means it's at the bottom. If it's 12 at the top, it means that it's top 12. So that is basically the way you could even imagine this is basically what the aquifer looks like. So gravity compensated is very important. But once you write into the file, you need to ensure that it moves back. So we basically did everything for Y0 matrix, X0 matrix, and DX cell matrix to ensure all of them are gravity compensated. Right, so after that, you are able to get some of the correlations between each cells. So we'll talk about this later on. This is just to initialize those ones to create the zeros, which is zero matrices. Now, this process here is going to assign the neighboring values of all the cells. How does that work is that you need to tell the computer where are those cells, how the relation goes. So let's say this is the first node, and this is the second node, for example. This is the third node, and here we've got the fourth node. Now, if we just copy the whole thing to another row, and you've got number 5, number 6, number 7, and number 8. Now, if you look at, so basically those are the indices for each node. Now, if you create cells, let's say if the cell is being here, right? So here we've got only 3 cells, 1, 2, 3. And we use red numbers to tell cells, yeah? So the number 1 is created by using a reverse anti-clockwise way, 1, 5, 6, and 2. Number 2 is made up of 2, 6, 7, and 3. So all those correlations is being done by these tiny little commands. Just leave that because it's already been done by itself. So we don't need to go to the details. So that's just, you know, for all the program, it has to be done in that way. And then, you know, if I do the 1 by 1, it will take like enormous amount of time because NEX is 150 and the NEY is 11. So what do? You just click continue. And then before you click continue, you put a red here. So you just jump quickly out of the loop to here. So it's relatively easy. So once you create that, you are able to get the X, Y element locations, right? So if you look at the X element locations, you will see that it will actually stop from the middle, so 0.5. Why it is 0.5? Because once we go back to here, so this is 0, this is 1, so the middle of the element is 0.5. That's right in the middle here. So that's basically create a X coordinate for all the elements. Likewise for the Y's as well. And remember, everything that doesn't have the gravity compensated needs to be flipped. So that makes more sense. So we have that one there. So that's basically the preparations. Now we actually start with the IMP files. So we first create our IMP file object. So then we give a title to them. And the version of Sutra is 2.2. It includes solid transport. It is 2D mesh and regular meshes, like a kind of grid meshes. And then the NN1 is equal to NY. That's the Y number. So the number of node in the Y direction, number of node in the X direction. So it's already been recorded. The n is the number of nodes and number of elements, so that's already been pre-calculated. So these numbers, NPBC, NUBC, these ones are the boundary conditions. So currently I set them as 0, but later on I will change it. I'll tell you how it's being changed. The simulation is going to be unsaturated, and it has to do a transient flow, which means you set a boundary condition to see how it's moved from the original boundary condition. And also the solute transport is transient. The code here means that it's not a start from a previous simulation. So it's starting from a code condition. And the ISTOR means that how often, after how many time steps, the simulation will be stored as a hot start. So we're not going to use hot start. So that dt is a very large number. Now we move to the up. Up is actually what we call a upstream or even downstream, upwind or downwind spatial discretization. So if your simulation is has a relatively turbulent flow, we suggest you use upwind. But for this case right now, let's just put that as 0. The GNUP and the GNUU are very important parameter. So if you look at the Sutra manual, you will see there are many documents about it. So what does this GNUP in particular mean? Is that when you try to apply a fixed head into a node, like a Mariotte bottle, you will have a conductance between the Mariotte bottle and the cell. And the conductance is basically to tell the resistance between the Mariotte bottle and the cell. So it's a little bit tricky here. You always try to ensure that the Mariotte bottle has got the same flow, the same pressure as here. But the problem is that if these two numbers are exactly the same, let's say 16 digital numbers, exactly the same, you will not be able to get a flow, because the flow is calculated by the pressure here minus the pressure there times the conductance. If the 16 digital numbers are exactly the same, you wouldn't have flow, right? But if your conductance is very small, you will see that the Mariotte bottle pressure is different from the pressure here, and then you're not really controlling the pressure here. So the good start point here is always use 0.01, but the actual number needs to be very well justified. So it's a bit numerical tricks to be able to get the right conductances here, but the starting point is going to be 0.01. Then we've got the number of schedules. We've only got one schedule. The NPCYC and the NUCYC tells you that how many loops you need to go after you run pressure and concentrations. So as we know, Sutra simulate two processes, flow and salt. So if you want to simulate salt, after the pressure is being run 3 times, you could try to change this into 3. So that means the pressure will run 3 times, and then concentration will run once. But we want to always do it iteratively. So pressure, concentration. So that means those are 1. And these schedules, you just leave it. Time steps, time cycle elapsed. So the scale is the time step. So that's 600 seconds. The IT max is number of the maximum time steps. So we basically allow the system to run 20,000. So in that case, the overall time to finish the simulation is going to be, so the simulation time is equivalent of 138 days, right? That's where you control the time steps and NT max. This number is a bit tricky. You need to ensure that your simulation is independent of this number. It has to give you same results. So the rest of them is to just values to make non-uniform time steps, so we just ignore here. For these numbers, you can just keep as it is. So this one tells you the external iteration and the criteria to consider the external iteration to be converged. So I suggest you to just use these values unless you are really struggle to be able to make your simulation converged. These numbers, I would always suggest you to use these numbers. I've never changed these numbers most of my time. So that's the internal converge criteria. And I sometimes find that if you try to increase this number, it will make your simulation not accurate enough. So always use that number. There are stories between these numbers, but again, you start off changing these numbers when you realize your simulation are always difficult to converge, but I normally don't change these numbers at all. Anyway, so these ones. And these are different types of output conditions. And nevertheless, this 1000 here means that the number of prints for the nodal results, you just use these numbers unless you really want to get some particular outputs to the system. So the 1000 is very important. So here it's got this 1000 is the number of print. And here is the output for the nodal data, which is NOD file. And that means that it prints every 500 steps. The negative here means that you allow the system to give you the default reading before it executes. And here is the type of outputs you would like to plot it to. So it's the number, X, Y, pressure, concentration, saturation, finished. So you could go to the modeling benchmark and open up the NOD file. Given that we've already done that, you will see the result is always being given as node X, Y, pressure, concentration, saturation. These are the extra output I created in SUTRASET, which tells you the precipitated salt, water mass, and salt mass. But just leave that for now. So here I've got the element extractions. So for the element files, you give the element number, the coordinate of the elements, the velocity in the X direction, the velocity in the Y direction, and finish the line. So then if you open it up, ELE file, which is here, then you will see that corresponds well with your request. So it's X, Y, X velocity, Y velocity, and I add the relative permeability in SUTRASET so that you can check whether the flow is being slowed down by the change of the relative permeability, which is again our extra function. Those are the outputs for different BC files, boundary files, BCUP, BCOF, this type of things. So I always make these numbers consistent so that when you look at the result at one-time snapshot, it always consistent across all those ones. So just leave that. So now let's move here. So this is the aquifer compressibility. The default value is 1 power negative 11. So that basically is to show if your pressure increase, your fluid will be compressed. But fluid is not really quite compressible. So this number is particularly important when your aquifer is confined. And this one is the heat capacity, so you just leave that one for 1. Sigma W, that's the diffusivity, which is the solute dissipation driven by molecular diffusion. I usually just use the original value, which is 1 power negative 9 meters squared per second. Give a good reason if you want to change it. And most possibly is that if your concentration gradient is very large, let's say if you have a salt front, a salt precipitation where the concentration is 300 ppt, then you probably need to relax this number a little bit, but in general, this molecular diffusion is 1 power negative 9 meters squared per second. Rho 0 is fresh water density. This one, you just leave it as it is. This 700 is to show how the density of water is increased due to the increase of concentration. So remember that fresh water is 1,000 kilograms per meter cube, and seawater is 1,025 kilogram per meter cube, and that is because this is calculated by 1,000 times 700 times the concentration, which is seawater concentration here. So that's 1,205 is calculated by that, right? Viscosity of water is usually 1,000 kilo per meter over second. Usually we don't change that number unless you have a compelling reason. For example, to simulate honey moving down to the ground. Compressibility for the aquifers is 1 power negative 7. That's always the number we've been using. And we have a lot of story on that. Again, this is important, particularly when your aquifer is confined. And the rho S is the solid density of sodium chloride, which is 2,600. And we've got the adsorption included. And remember, this adsorption, we put it as none because we're not really simulating the adsorption processes of salts attached to the solid grains. So just put a none there. And if you want to simulate, for example, salt precipitations, we usually use Frederick with this set of chi numbers. This is a production of solid and energy, so just put them as 0 for this case particularly. So those are the gravity directions. Remember that the gravity is considered in the y, and then it's in the reverse manner. So it's pointing down, so that's why it's a negative 9.81. So leave that number, pretty much never changed, unless you want to use z to look at the gravity impact. So now we move to the node-wise data. So you've got overall scale, x and y and z. So that's all 1. So we don't want to change everything in a scale-wise. So overall scale. Here we've got just all these data that are able to be used. So the IMP, II, remember, are the node indices. So we create this one to create that. Remember, this II needs to be a column rather than a row. That's why we first create a row and later on use apostrophe to change it into a column. Then we want to have a NREG. NREG is basically to tell which set of permeability and soil water retention curve parameter to be used. So we probably can open up a NREG file. So part 1, IMP. If you open it up, that's basically where the dataset 14 is. So this NREG is here. So that's the node number, 1, 2, 3, 4, 5. This is NREG. So this NREG will tell you what unsaturated permeability you are going to use, and the soil water retention curve. Basically, that differentiate different types of soils, right? So clay and silt, clay, silt, and sand has different unsaturated permeabilities to be used. So I'll show you that later on. But by default, all of them are 1. And then the X is going to be the X naught array. Remember, this is not gravity compensated. It has to use that number. And the Y naught array. And now remember, we discussed about the Z is going to be 2 pi and the X location, right? And remember, I always have a small number here to add it up. And that is because I don't want to have the first Z as 0. because if you have a 0, that really means this cell is infinitely small. So I always make a small number. You can put it as 0.01 or something. It's just to ensure that the first row has got a finite size. The porosity originally is 0.43 for all the cells, right? Now, we create the scaling numbers for dispersivity and hydraulic conductivity. Literally, it's permeability. And we also create a the node numbers, element indices, and the element tags to see whether it's sandy soil, sealed soil, and clay soils. Now, this is a bit tricky part we need to go through very, very quickly. So Pmax means the maximum permeability written in the matrix form, and it has to be gravity compensated. So first is that we create a matrix with the same size as the matrix here, plus the sand, right? So if we run this command, so basically this, so let's first run over here. So let's continue. Okay, let's continue here. So if we run this line here, it creates a 0 matrix, all zeros. But if we add the permeability of the sand, it basically shows all the variables. It shows that all the elements within the matrix is the same number, which is sand. So that's basically the same. So that means the whole aquifer is sand. But that's not true, because the top layer, when the Y is greater than 0.6, it's actually sealed. So to be able to hatch all the sealed layer, we use this. So that's Y element matrix gravity compensated is greater than -6. So that's basically give you a mask. The mask is tell you that only the top ones is where the sealed is located, and that is 1, and the rest of them is 0. So if we, so basically the mask element matrix sealed layer gravity compensated means it's a mask matrix that highlights all the sealed cells, right? Now, once you create a mask matrix, you want to assign a permeability to a different value. So that's the permeability of the sealed layer, which is that small number, right? So originally, all those values are the same, right? But if you hatch them by a mask and then give a different number, then you will see that the permeability is different now. So the bottom layer has got a relatively high permeability, whereas the top layer has a relatively low permeability. Yeah. So that's the very, very useful function in MATLAB to help you construct your model. So we always use this kind of tricks. And remember, this is gravity compensated, but it doesn't show the way how the code is being stored. So you need to convert it back, which is to flip it, right? And then you've got the Pmax array matrix by convert this matrix into an array, because in the computer, everything is stored in the array. And then that means that we create a Pmax array to be able to be stored. And then we use that to assign into IMP dot Pmax and PMIN. So that's being stored. And here, this section here is to show the dispersivity. So that's the longitudinal dispersivity is 0.5. And the transverse dispersivity is 0.5 as well. Usually you will find in the literature this number tends to be a tenth of the longitudinal value. But for now, we just basically showing the process. So either numbers are fine. Now which one we are looking for? So this would be mask matrix. Well, that's actually the advantage of using a long variable so that I know, because this is 2 months ago and I probably already forget about that, but I'm trying to get this idea. So this is mask matrix, which is related to node, and it's a matrix. So that's called the aquifer boundary, and it's gravity compensated, which means it shows what really looks like. So what are the locations is that the location needs to be, the y elevation is less than -4, and the x is greater than 149.99. Okay, so if I look at this condition, I know this boundary, if we go back to the sketch here, represents this line, the line on the left-hand side here, which need to assign a pressure, right? So if I run this command, we will be able to see only the boundaries at the left-hand side. So let's run this command and see. So I use that, put it in here, and you will see only the left bottom has got 1. That's where the location is. So the advantage of using this method is that if you try to increase it, you just try to change this -4 and then that hatch different numbers. And then once we add that one there, we are able to create a index array. And then by getting that array, we are able to calculate the PBC there, which is a complex function here. So this function here shows how the pressure is being calculated based on this trapezoid. So initially you got a small pressure and that increases, and we also add the density impact there as well. So that shows how this trapezoid is being implemented. And if you want to use different elevations, you just need to change that function. So now let's keep going. So this one has got what? Mask, not matrix, aquifer boundary, gravity compensated at the top. So this is actually, if I look at this variable, which well is very long, but it helps you to explain what happens, is actually here. It's here. So the way how we find it is that the y needs to be greater than -0.1, and the x is less than the point radius. The point radius is 100, remember? So if you run this command, you will see this mask is only near the top. See, that's where the point is located. And then we basically store that into a separate variable and use it later on. And the porosity, remember that the porosity for the sealed is going to be a small value, So first is that we need to hatch all the y that is less than 0.5 meters, and the y that is greater than -8. So that's where the sandy the sealed layer is located. So it's higher than -8, less than 0.5. So that is actually in this section. And we create a porosity matrix, and within the matrix, we ensure that the sealed layer hatched by 0.03, and the rest of them is the base number 0.43. So essentially, the porosity within this layer is 0.03, and the sandy layer is 0.43. So we could run that through, and then we can check the porosity here. So to be able to check the porosity, we just, no, probably not this one because it's not pressure compensated. So that is the relatively easy one to look at it. So essentially, for the sandy aquifer, it has got a relatively high pressure porosity, and for the silt layer, it has got a very small porosity because that's where the water goes through, and top ones has got 0.43. Now, we keep on using the pressure. So now we moved to the pressure boundaries. So the pressure boundaries is being identified first by the IPC node matrix. So that's here. Remember that this is where the aquifer boundary condition, which is here, right? So that's the number of the node indices. And we also assign the pressure, and also the concentration is going to be seawater. That means we basically put a Marriott bottle here, and it has got this type of pressure distribution. And if the water gets in, it's going to seawater by this few lines. And so this is in default for the IIN, so we just leave that. And the IIN is basically the correlation. Remember the correlations of each cells as shown by this cell. So if it's element 2, it's made up by number 2, number 6, number 7, and number 3 in the anti-clockwise manner. And then we are able to save things into a file, which is IMP. So we basically gone through all the IMPs. Now we need to look at the initial conditions. So initial condition is saved in the ICS file. So first is that we need to create the initial head aquifer. So let's run that. So that's the P pressure. So you can see that this is basically hydrostatic distribution. So water level is just here. It's where the 0 is. But remember that the silt layer has got very, very dry soil. So in that case, we need to apply a suction that is extremely high in the silt layers. And that's why we need to create a mask for node matrix silt layer gravity compensated. And if it's in that location, then we need to assign that into a very, very small pressure. So now if I run it again, you will be able to see that the pressure. So so for this line, it basically just change the This is to change the pond water level. So the pond near the surface. So when you look at the surface, this section where pond is located is no longer a negative number anymore. So if you move further down, so that's the intersection between the pond and the beyond the pond. So that area is changed to a positive value, suggesting there are water inside the pond with an initial height of 0.5 meters. And then we are able to produce a PM out of that. Now, if we look at the concentrations, we basically use the same way. So the concentration for the whole sandy aquifers as a hypersaline, but for the silt layer, it's actually fresh. And we could check from the gravity compensated, you will see that the sandy aquifers has got the relatively high salinity, whereas the silt layers has got a relatively low salinity. But those things are always be able to be changed if we have to. All depends on the calibrations. So, and this is the original time. and then we can basically finish the creation of the input files. Now, if after we run this, then we will be able to run the program. We've already run the program, which lasts about 3 minutes, so we don't really have to run the program again. So let's assume that the run SUTRASET has already been done. Then we can do the readings, right? So this reading basically reads all the files into the MATLAB so that you can do the plotting. So you got the IMP file, NOD file, ELE file, BCOP and BCOF, and all the indices where the concentrations are located. It's very straightforward. And then we can plot the result using the SL analysis. And I don't need to go through that in the details because it's just the plotting tools. And in the end, you will be able to produce a result similar to that. So the analysis has got all the detailed functions to show a fixed point change over time. So that's got 3 points over time. It has got the contour plots plus the change the profile over time. So just go through that in details, then you will be able to see how the result is being extrapolated. Before I finish, I need to go through one of the extra input file, which is very, very important. That is particularly for SUTRASET. This file is et.imp file. So all the things that is being hatched is just the comments, so just ignore about it. But some of the things are very useful. So let's say MET-MAR. The MET here means that what type of evaporation method you've been using, but currently we are not really using it. What type of aerodynamic resistance are you using? What type of surface resistance are you using? And what type of salt resistance are you using? So that is not really quite important for now. The key thing, particularly for the case where evaporation is not considered, is the soil water retention curve. So this line here. So that's here. We just find out the line that is not being hatched. Okay, so you've got 4 sections. So all the variables end up with 1 is a pair. So SWIES is residual liquid water saturation. AA1 is the air entry pressure, the reverse of the air entry pressure. And the VN1 is related to the pore size distributions. And we know that this number are always different when the soil type is changed. So this is the second type of soil. So we need to ensure that within the NOD file, so LREG and NREG. So if we go to the IMP files, what type of soil water retention curve that we use? So currently they are all 1 value. It doesn't change, but if you want to change from sand to silt, you need to change the LREG and NREG value accordingly so that they use different soil water retention curve. And that's about it. Thank you.